Welcome friends to my YouTube channel Sommo Physics. So in the previous lecture we have discussed about the derivation of various properties of central forces. Okay, now in this lecture I am going to discuss the equation of motion of a particle in a central force field. Now let's start. Before I start, I would like to tell you that if you don't subscribe my channel, kindly subscribe my channel and share it to your friends, neighbors or relatives. So let's start. Now if a particle of mass m, say, lie in a central force field, say particle of mass m lie in a central force field, then we can write its kinetic energy as half m r dot square plus r square theta dot square. Obviously this we can write by using polar coordinates. Okay, so if a particle lie in a central force field, say of mass m, then we can write its kinetic energy as this by using polar coordinates. Now potential energy of the particle we know in generally is a function of position. That is, we can write V, this is equal to VR. So this is the potential energy. Now what would be the Lagrangian of the system or the particle? At first we have to find out the Lagrangian. This is T minus V. So we can write this half m r dot square plus r square theta dot square minus VR. So this we can write down the Lagrangian of the particle. Now from this equation we can find two equations of motion. One is radial equation of motion and another is cross radial equation of motion. And how? First of all, what is del L del R dot? My del L del R dot will be m r dot. Now what will be my del L del R? My del L del R will be m r theta dot square minus del V del R. So what will be the radial equation of motion? We can find it in terms of Lagrange's equation of motion for a conservative system, that is d dt of del L del R dot minus del L del R, this is equal to 0. So we can write as d dt of mr dot minus mr theta dot square plus del V del R, this is equal to 0. So this we can write as mr double dot minus mr theta dot square, this is equal to minus del V del R. So this equation can be written as m into r double dot minus r theta dot square equal to f of r. So this is the radial equation of motion of a particle in a central force field. Okay, so this is the radial equation of motion. Now what is the cross radial equation of motion? Again we have to find out del L del theta dot and del L del theta from this equation. So from equation 1 we can write del L del theta dot, this is equal to m r square theta dot, and del L del theta, this is equal to 0. So what will be the cross radial equation of motion? That is d dt of del L del theta dot, that is mr square theta dot minus del L del theta, which is 0. This is equal to 0. So from which we can easily write mr square theta dot, this is equal to L, this is equal to constant. Okay, so these two, that is the radial equation of motion and the cross radial equation of motion, okay, they are known as the integrals of motion. Okay, more commonly they are known as the integrals of motion. Okay, integrals of motion, integrals of motion. So in this way we can find out the equation of motion of a particle in a central force field. One is radial and another is cross radial, and more generally they are known as integrals of motion. Okay, now we have previously told that the energy of a particle in a central force field, total mechanical energy of a particle in a central force field, remains constant. From this equation we can prove it. How? First of all, we write down the radial equation of motion, that is m into r double dot minus r theta dot square, this is equal to f of r, say minus del v del r. Now multiplying both sides, that is mr double dot minus m into r, what will be my theta dot? We write L equal to m r square theta dot. So from this equation we can write theta dot as L by mr square, that means L square by m square r to the power 4 plus del v del r, this is equal to 0. Okay, now m into r double dot, this we can write minus L square by mr cube plus del v del r, this is equal to 0. Okay, now this term can be written as del del r of L square by 2mr square plus del v del r, this is equal to 0. Now multiplying both sides by r dot, so what we get, m r dot r double dot plus this will become del del t of L square by 2mr square, and this will become del v del t, this is equal to 0. Okay, now this can be written as del del t of half m r dot square, okay, plus del del t of L square by 2mr square plus del v del t equal to 0. So in general we can write d dt of this total sum of three terms, half mr dot square plus L square by 2mr square plus v, this is equal to 0. So this term is constant, and which is nothing but the total energy. This term represents the total energy of the particle in a central force field. The first term represents the kinetic energy, second term represents the centrifugal potential energy, and the third term represents the ordinary potential energy, and these two terms are the total potential energy. This is called centrifugal potential energy and this is called ordinary potential energy. Okay, so thus we see that the total energy of a particle in a central force field remains constant. Okay, so first we have find out the equation of motion of the particle, and from this equation, that is by using this equation, we prove that the total energy of the particle remains constant. Okay, thank you.